Greetings. So, the Egyptians did very practical math, not dealing with the theoretical that well. Let me give you an example, please. The Greeks are all about understanding why something works. Can you show that it always works? The Egyptians were very much about, did you get an answer that's close enough for us to do something practical? Let me give you an example. We know from one of the papyri that if you give me any four-sided figure with the lengths of the sides A, B, C, D, the Egyptians said no problem, the area will be equal to A plus C times B plus D, and then you basically have to do some division because you've got too much. And so we're going to divide by, let's see, I've got twice what I need here and twice what I need here, divide by 4. And that might work. Let's take a look. If I have a perfect rectangle, we know that the area of a rectangle is length times width. All right, so let's go ahead and put some new letters up here. W, X, Y, Z. So we know the area here will be equal to W times X. Now then, let's apply what the Egyptians thought they should do. They would take W plus Y, and they would take X plus Z, and they would divide by 4. So this right here is the Greeks. This is the area according to the Egyptians. Now, with the Egyptians, I know that W and Y are the same, so this becomes 2W is now multiplied by 2X over 4, which is the same thing as saying 2 times 2 is 4, W times X over 4, which is W times X. Hey, for a rectangle, it's a very good methodology. The problem is when you lose these right angles, will this formula still work? Length times width. And I hope your insight is strong enough to say no, it won't. The more I deform this, the less likely length times width will work. Take, for example, a parallelogram. And if I really bend over a parallelogram, there's no way that saying X times Y is going to be the area. You have to figure out this height. The Egyptians weren't figuring out the height. They were saying, take the side, don't worry about it. Because most probably in Egypt, they were trying to make as close to rectangles out of every four-sided figure they could. Well, in that case, you've got a very practical solution to a group of problems. Namely, how much land area do you have? Therefore, how much am I going to tax you? And in this case, what I mean by taxing is, at the end of the growing season, how much grain do you have to turn over to the central authority so we can all eat all winter long? So if this is how you're doing things and you're going to base how much grain I turn over to storage, it works perfectly spot on if I have a rectangle, but if I have this shape, you're going to overtax me by a lot. Matter of fact, I might owe you more grain than I can actually grow on the piece of ground that I have if you're using this formula. So, practical math versus theoretical math. The Greeks are very much in why does it work? And they will come up with these definitions and discussions in Euclid's Elements where they explain why things work. The Rhiine papyri give us examples out of history where the Greek or the Egyptians were simply kind of playing around with numbers and getting close enough and being happy with it. This is also another reason why I will make a claim. No way that the Egyptians would have had a very good understanding of pi, because their practical nature would have said, who cares what the exact number is? It's somewhere around 3, and that's probably close enough for everything we're going to want to do with it. And to be honest with you, civil engineers even today probably only need to use 3. If they're getting real precise, 3.1, and you're close enough for most projects you'll ever build in your life. The practical nature of things is so much different philosophically than the theoretical. We in math love to talk about the square root of 2 and these exact answers that we get. And that's all good here in academia. But when you get out in the real world, don't ever forget, even though the Greeks give us our theory, we very much still have a practical universe we have to deal with. And that means we have to deal with an Egyptian history as well. Is my answer close enough that I'm not worried about the little bit of error that I'm going to have? I'll tell you now, for most of what we do in life, we're a lot closer to the Egyptian tradition than we are the Greek tradition. It's only in our pure math courses that this tradition is what we still uphold to the letter, beyond a doubt. I hope this puts some explanation behind the difference between theoretical and practical math. I hope this helps.